So hello students, welcome you all on this YouTube channel. So phasor of ideal transformer we have seen, we will see now, right? So we have drawn the phasor diagram of practical transformer till now. Now our aim is to draw the phasor diagram of ideal transformer, right? So what is ideal transformer? To understand ideal transformer, first just have a look at it on practical transformer, right, that we use, right? So practical transformer is having a leakage reactance x1 and x2, right? Practical transformer has losses, hysteresis loss and core losses. RC is the representation of core loss. Practical transformer require the sufficient MMF to establish the flux in the core, right? For that you have Xm, right? Similarly, practical transformer has winding resistance, non-zero value of winding resistance. Practical transformer has non-zero value of winding resistance R1 and R2, right? So practical transformer is having winding leakage flux also. Correspondingly, you will have a leakage reactance. Leakage reactance is the representative of leakage flux. So in practical transformer, since leakage flux is not zero, that's why you will have x1 and x2 leakage reactances, right? Practical transformer is also having hysteresis loss. It is also having eddy current loss. Losses are not zero in practical transformer, right? So this is the practical transformer equivalent circuit that we have studied in the last video. Now if you want to study the ideal transformer, then what is the ideal transformer? So any transformer which is having these four conditions, which is satisfying these four conditions, will be called as ideal transformer. Number one, ideal transformer is having no winding resistance. Winding resistance will be zero in ideal transformer. Number two, in ideal transformer there will not be any winding leakage flux, that means no winding leakage flux. Number three, in ideal transformer there will be no hysteresis loss and no hysteresis loss and no eddy current loss. Number four, ideal transformer is having a core of infinite permeability, right? Now core has infinite permeability in ideal transformer. What is the meaning? Meaning is that negligible MMF is required to establish the flux in the core in ideal transformer, right? So MMF is basically flux into reluctance. You know that in magnetic circuit we have studied that the basic fundamental is that MMF is basically equal to flux into reluctance. Reluctance is inverse of permeance, right? So if permeance is infinite, then reluctance is zero. So that means MMF required for ideal transformer is zero. That means negligible, almost zero flux is almost a zero MMF. Zero MMF is required to establish the flux in the core in the ideal transformer. So ideal transformer means no winding resistance, no winding leakage flux, no hysteresis and eddy current loss, and core has infinite permeability. So such transformer is known as ideal transformer. So if you see the circuit diagram of ideal transformer, it will be like this. Just remove R1 because winding resistance is zero, so I have removed R1. Similarly, remove winding leakage reactance, so remove G times of x1, right? Now negligible MMF is required to establish the flux in the core, so magnetizing reactance you just remove it, that is not required, it is negligible MMF, right? So remove Xm, and core loss is also zero, so remove this RC, this is zero, so remove this shunt branch, this whole shunt branch, remove X1, remove R1, right? Similarly in the secondary side, remove R2 winding resistance, remove winding leakage reactance X2, right? So if you remove all these things, you will simply get this circuit like this, alright? So this is a circuit of ideal transformer, right? This is a circuit of ideal transformer. Now how to draw the phasor diagram of ideal transformer? Just have a look at it. First, now you see that in this circuit you have only ideal inductor with zero resistance. So for pure inductor or ideal inductor, the current will lag the voltage, the respective voltage, by 90 degree, exactly 90 degree it will lag. So if you draw the phasor diagram, you can simply draw this. I'm going to draw here, right? I'm going to draw the phasor diagram of ideal transformer here in this space, right? This is the phasor diagram, is basically representing the phasor diagram of ideal transformer, right? And not for the practical transformer. Practical transformer phasor diagram we have already drawn in the earlier videos. So this phasor diagram which I am going to draw now is basically phasor diagram for ideal transformer only, right? So V2, draw reference phasor V2. That is the first step in every phasor of transformer. So V2. Now you see, apply KVL. If you apply KVL, then you get V2 is equal to E2, right? So this is a phasor of V2. So now take I2, that is 90 degree lagging, because it is now ideal inductor, pure inductor, right? So this is I2, it is 90 degree lagging by this voltage V2, right? Now, so in the next step you draw this E1. Let us suppose E1 is less than E2, because because we have assumed that N1 is less than N2, number of turns of the primary winding. If it is less than number of turns of the secondary winding N2, that means if N1 is equal to N2, then definitely magnitude of EMF will be less than magnitude of E2. So E1 is less, E2 is more, right? So draw E1 here, right, on the same line. Now in the next step, draw the, you know that flux and EMF both are in phase quadrature, right? So just draw this mutual flux phi m, right? Phase quadrature means 90 degree phase difference, right, between flux and EMF. So d phi by dt is the induced EMF, right? So from flux you will get induced EMF. So induced EMF will be lagging flux by 90 degree, or you can say flux will be leading the induced EMF by 90 degree. You see this, right? 90 degree, right? So in the next step you have to draw the this I2 in this side, back side. So it will become I2 dash, which is nothing but I1 only, right? See this is the current I1, and here it was I2 dash. So shunt branch is ignored, so that means I1 is equal to I2 dash. This I1 is equal to I2 dash because the same current will flow here, right? I1 is equal to I2 dash because we have ignored the shunt branch. So I1 is equal to I2 dash because the exciting current is 0, right? In practical transformer you have I1 is equal to I2 dash plus IE. So exciting current is almost 0 because we have said that negligible MMF is required to establish the flux in the core. So IE is 0. So that means you simply write I1 is equal to I2 dash. So I1 is equal to I2 dash, right? In the next step you draw this line like this. This is basically the representation of minus E1, which is basically V1 dash, right? So that is basically the phasor diagram of ideal transformer. All right. So if it is ideal transformer, since it is ideal transformer, so winding is purely inductive. So I2 will lag by V2 by 90 degree, exactly 90 degree, right? So that's a phasor diagram, right? Obviously these are all phasor values, mind it very clear, because we are dealing with AC, right? I repeat this phasor diagram once again. In step number 1, draw this V2, take V2 as a reference phasor as earlier. So V2 is reference phasor, so draw V2 horizontally in step number 1, right? Now apply KVL in this loop, you will get V2 is equal to E2. That means in the step number 2, draw E2. In the third step, lag I2 by 90 degree, right? Lag I2 by 90 degree from V2, because winding is purely inductive, because it is ideal transformer, no winding resistance, right? It is purely inductive, so I2 will lag V2 by 90 degree, so I2 will come here at 90 degree. That is step number 3. In step number 4, draw E1, right? E1, since we are assuming N1 is less than N2, so E1 is less than E2, so E1, magnitude of E1 is less than magnitude of E2, right? Step number 4, right? That was step number 4. Now step number 5, draw phi m. Draw phi m. Phi m is the mutual flux in the core, which will lead the induced EMF by 90 degree, or you can say EMF will lag this mutual flux by 90 degree, because d phi by dt is induced EMF. First you will get the flux, then you will get the induced EMF. So induced EMF is lagging flux by 90 degree, right? In step number 5. In step number 6, you have to draw this I1 is equal to I2 dash. I1 is equal to I2, take I2 backside, so I2 dash, that is equal to I1, right? From here it is clear, I1 is equal to I2 dash, because I is 0, so I1 is equal to I2 dash, because we have ignored the shunt branch. That was the step number 6. I2 dash is equal to I1. Now last step is the 7th step. In 7th step, take E1 in the backside, that means minus E1, that is equal to V1 dash. That is step number 7. So that's how you draw this phasor diagram of ideal transformer. This is the phasor diagram of ideal transformer, right? Phasor diagram of ideal transformer, right? So thank you very much. Thanks for watching.